identify how things are going to fail.
All right, let's get started. Can you hear me reasonably well?
Clear. I'm on fire.
Okay, welcome to the CCWG meeting at IETF 125. This meeting is being recorded, and make sure that you've joined in Meetico, especially if you're in the room. So you're gonna need to join the queue with the queue button. If you're remote, you can send audio with the microphone buttons, same as usual. Yes, Martin, Eric is muted. The microphone should not be muted. Hi, there's the other camera.
Well, I think someone was saying that, ask them if they can hear.
How well can you hear? You cannot hear in Shenzhen. Can remote folks hear?
Yes, we can.
Okay, sounds like we need to.
We looks like Jonathan is speaking, but we can't hear him.
We can't hear Jonathan either.
I'll page Meetico.
Thank you. Give them a brief. Cool. Reese just did.
Wow.
Yeah, that works. See if we get an act for that. Oh.
Ah, there we go.
That sounds promising. You can hear us. Sweet. All right, much success. Let's keep going. This is the part we need to make sure we cover anyway. This is the IETF note well. These are the terms under which we participate in the IETF. Note that we operate with a code of conduct. If you observe any violations of that code of conduct, please reach out to the chairs, the responsible entities, or the Ombuds team. Please also take special note here of your IPR declaration requirements. The moment you become aware of some IPR relevant to what we're talking about here, there are some obligations for your disclosure of that. So please make sure that you've read the relevant documents. Yeah, we're getting some of the echo too. Got some helpful links here, mostly for clicking later. And this is our agenda for today. So we have a super packed agenda. So we're going to try to make it zippy as we go through. Please try to keep your comments when you're in the queue as concise and useful as possible. We'll be using the timer. And our first topic today is the rate limited document. This is more of a call to action. There were a couple of non-trivial changes that happened during and after the last call. So we don't have slides for this because it is explicitly a request to go please look at the latest version of the document rather than a slide version of that. But just a quick heads up to the working group, and this is also there on the list, that there were some changes that happened there. So go take a quick look. Just to make sure that things are still in good shape. Any questions there? If not, we should have an Ian. I do not yet see an Ian. There's an Ian.
Hello? Can everyone hear me?
Yes. Take us away with some DVR.
Oh. Thank you. You're going to present for me, I guess, right? Yes?
Yes.
Oh, great. Okay, next slide. Yes, so we've continued to make excellent progress and just kind of closing out some minor issues. You can, oh, I can advance, never mind. Yes, there are 3 open issues. 2 of them are relatively minor. One of them is more substantial. And you've seen these slides before, but this is just a reminder of, if you want to read the most recent editor's copy of the draft or file issues online, then this is where to go. So in this update, there are some logic updates that have occurred. In particular, this kind of a refinement to the pacing text. I think that was written by Neil with help from Christian in particular, so thank you. It's also some behavior about various TCP specific behavior. Sorry about that. And some loss recovery, in particular, if SAC is not available, what to do. Obviously, you would like to have SAC available, particularly with BBR. It is definitely not optimized for cases when SAC is not available, but we at least need to specify what the algorithm should do in such a circumstance. And we said there's an open issue about kind of what happens if you get stuck in drain forever. And in the end, we decided to exit drain after 3 RTTs if you hadn't fully drained the queue. The math indicates that you should have more than drained the queue by 3 RTTs, but we didn't want to have a situation where you just got stuck in the same phase forever, and because some other issues could arise. So those are the actual technical, like algorithmic changes. If no one has questions, I'll keep going. Great. So we have a number of editorial changes. We continue to try to remove TCP-specific stuff from the draft. We are making excellent progress and have removed almost all of them at this point. I add some text on offload budget for Quick in particular. It's slightly different from TCP, but in the same spirit. And then there were a variety of kind of pseudocode sort of fixes just to make sure things actually worked out. Arguments were aligned and so on and so forth. Naming was correct. So anyway, I should go back. So as you can see, at this point, we're really mostly getting into the fine tuning of the draft. I don't think any of these changes are considered enormous. Certainly, if any of the functional changes, you take a closer look at them later and you find that you don't like them or they're concerning, then we can revisit those. But I think most of them are fairly safe. So I started writing a PR to add test cases. I have not finished that PR, so that's on me. But there's still kind of a hope to at least write up in broad strokes what the key test cases we think are that should be tested for to ensure that you don't hit kind of some fairly common pitfalls that other implementers have hit. So this is really very much an effort to define all the cases that might otherwise cause you to say, my BBR didn't perform very well. Why is that? And instead of one of the other people who implemented BBR having to come to you and go through your code with fine-tooth comb, if you think you've passed all these test cases, then hopefully there are very few remaining kind of gotchas that you could hit. So, but that is going to happen soonish. And the other issue, the non-TCP aspect, as I said, we made a lot of progress on this. It's not quite done, but it's getting very close. And the third of the 3 is kind of a purely editorial issue that I think Martin Seaman filed. So thank you. Thank you for the generally thorough review from Martin. So yeah, at a high level, that's where we are with the issues. There are a few things still hanging around, and they have been kind of around for a while, like this ACT phase PR. And I think we discussed this at a past IETF, and this is mostly a case of we think this is a safe change, but we need to verify. And there's this much more complicated issue, which is kind of a restart from idle issue. But again, we have discussed this to some extent at a past IETF. So unless someone has particular thoughts on either of these 2 issues, which you're welcome to comment today or comment later on the list. But I guess neither of these are particularly new. And yeah, so I realized that was a little bit faster than scheduled, but hopefully the direction we're going is kind of what the working group is expecting. And but if there are any questions, comments, suggestions, please come to the mic or feel free to come on the list or afterwards. Or if the chairs have any questions or comments, that's also welcome.
All right, thank you, Ian. Do we have anybody, I know in past IETF meetings, we've had a couple of the different folks who are working on implementing here, kind of give quick updates as to how things were going there. If there aren't specific folks who want to join the queue to talk about any of these particular PRs, are there any folks who are currently or have recently been working on implementing that would want to chime in? We have a Gory.
Hi, Ian. Can I ask about analysis of the method? Has anything changed in the method that needs to be looked at when we do the implementations and we benchmark them?
I don't think the changes recent are likely to meaningfully affect like kind of the simulations and analysis. That being said, you know, I think more simulation and analysis, I don't think that would be bad. I think it's been looked at a fair amount at this point. But I don't really expect none of these changes are like probably even likely to occur in any of the test cases that you would typically test, right? So.
Yeah, okay. Thank you.
Thank you, Gory. Anybody else want to chime in, or shall we, Ingmar?
Yeah, no, thanks for the update. And I wondered when I last reviewed this draft, I thought that there was some external publication around the testing of BBR, and some results look good, some results look like room for improvement. Did you have time to look at it, or I don't remember the link to it anymore? But
I don't think I know what you're referencing. I can't remember off the top of my head. I don't know if Neil or Joseph are on and remember. I apologize.
I'll try to dig it up and see if I find it. So.
Yeah, can you guys hear me? Hello?
Yes, we can hear you. Yeah. Oh.
Yeah, I believe there was a paper that you might be referencing that was called something like Promises and Potential of BBRB3. It does discuss I think the main interesting part was discussing the coexistence between BBRV3 and cubic, and comparing it to the coexistence properties of BBRV1 and V2. You know, we are aware that the coexistence properties are not as good as we would like. And in some cases, they can be slightly worse than BBR V2 due to the nature of the bug fixes in between V2 and V3. We are, you know, it's something we continue to do R&D work on the algorithm, and we're open to suggestions from the community. Yeah, I think that's the sort of quick summary.
Antonio Cloudflare. I was actually wondering about implementation experience with the probe up changes that happened probably like a year and a half to 2 years ago, where like the probe up phase mimics the startup phase exit instead of like some other logic. It seemed like an interesting change. I wanted to some extent we can actually do the same kind of thing in other places, like between drain and probe down, to other some of the other issues that like being talked about in various places. But again, like any implementation experience that you can share on probe up.
I actually think Neil might have the best data on that, on the probe down and kind of combining those two phases. Yes, the authors have discussed that a few times, and I think our inclination was we have a fair amount of shipping data and experience with something that looks like what's in the draft today, and you know, trying to make the algorithm simpler. That's like the pro and a con. One is like, yes, conceptually it's like actually quite a bit nicer, and the same thing for probe up. But on the other hand, it's like how much data do we need to like be comfortable that those like algorithmic simplifications are like safe in whatever ways we want to define safe. But I think, yeah. Oh,
Yeah, in terms of implementation experience with the newer ProBop, that is the code that you see, or the algorithm that you see in the draft, and the code that you see in the TCP BBRv3 code on GitHub is what we are using at Google for both internal and public internet WAN TCP traffic. So we have a fair amount of experience with it and think it performs pretty well. But are always open to hearing people's test results or analysis results if folks are seeing issues. Is that helpful, Antonio? Did you have another kind of perspective that you were hoping for?
That's good. I just wanted to actually like get the discussion somewhat started on some of those things. I haven't looked at the kernel implementation. I have looked at multiple quick implementations, and they vary in what they actually end up doing here. Just trying to figure out what's actually better and like how different are they.
I see. Yeah, I haven't looked at other implementations, so I don't know what variations people are trying. But if someone wants to summarize those on the mailing list or in a GitHub issue, we can discuss our thoughts on the various twists that people are experimenting with.
Hi, Lars Eggert, Mozilla. So I don't have a specific comment. I just wanted to like thank everybody for keep pushing on BBR. We don't really have started an implementation, and I'm still sort of personally hesitating to commit at this point, but it's clear that it's getting better, and it's getting to the point where we have a document that you can just implement and be reasonably sure that you're not going to sort of shoot yourself in the foot. So that's great. So we're looking with interest, and don't take silence for no interest. Thank you.
okay. I think that's it for me, unless the chairs want to have anything to say.
Thank you very much. I think that sounds like we're in pretty good shape. As we look at some of our, evidence of safety and things like that, obviously the fairly large deployment that currently exists is pretty good evidence. But we'll kind of work through that with the rest of the working group as we start to try to converge on closing down the remaining issues and stuff. But thank you very much for all of the great progress here. All right. I believe that brings us to Ingmar.
Thanks. You hear me well, or?
Yes, we can.
Yeah, thanks. This is an update to the Scream version 2 algorithm since the last IETF, and it's in version CF7, and it's me, Magnus, and Mirja who are authors of this draft. And I guess we can take the next step. And next slide here, please. Or should I forward myself? Sorry. Yeah, and the basic function with Scream is that you have a network congestion and transmission control, and on top of that you have a media rate control. And these are implemented in a draft in like you need to have both in order to make it work well. And you have the network congestion controller has both a packet pacing and you have a window based. So we go between being window limited and kind of rate based on the packet pacing rate in the algorithm. And the thing with the Scream here is that you have, instead of having congestion window that limits puts a hard limit on how many bytes in flight that you can have. It's like it's typical, for instance, TCP algorithms. You have you have the ability to make it go beyond the reference window in this case, which is like a congestion window, but we call it reference window to avoid confusion. And this avoids that you get an unnecessary sender queue of large video frames that can occur occasionally. Not just iframes, but also other like P frames that can be unusually large for the moment. And what is new in this latest draft is that you may make this overhead adaptive, depending on if you're in congested state or if you're in uncongested state. And the reference window increases a bit like normal TCP Reno, for instance. You have an additive increase, multiple decrease in some sense. And if you're there is some it mimics TCP cubic in some sense. If you are close to the last known maximum reference window here, you can limit the growth. And if it's long since you're congested, you can end up in a state of a multiplicative increase as well. So you can ramp up faster to free capacity. And what is new in the version 2 is you have additional restriction when you are congested also to avoid you get large variation in the reference window and queue delays. More on that later on. And the reaction to congestion is a combination of if it detects packet loss, ESGN mark, or L4S congestion marking. And also if you get the queue delay increase. Packet pacing is typically used, and then you normally pace at 150% of the target bit rate. But that can actually be increased if you're in an uncongested state. For the media rate control, you have that the objective of this media rate control is just to maintain just about enough data to fill the available capacity. And this actually poses a bit of a challenge because you end up, you often switch between a rate limited and a congestion limited state if you're in a congested state, network congested situation. So you want to avoid that you fill the data unit queue in this case, or RTP queue for that matter, with unnecessary data, because then you increase your end-to-end delay. And the target bitrate is typically quite simple to implement, but there are some extra things to avoid that the queue delay, the network or the sender queue delay grows too much. And challenging part is that the real-life media encoders are kind of a slow rate control loop. And also one thing is that you have large iframes at each group of pictures interval that they can be much larger than the nominal frame size. And for that matter, things like gradual decoder refresh is highly recommended for these applications. And sometimes the media rate is not exactly like according to target rate, not even on a average perspective. So that is things like you need to address. And one thing with the media rate control is that if the sender queue grows too much, like you get more than 100 milliseconds worth of media data in the queue, then it can actually discard the frame, because then that data is already useless for the receiving endpoint, and then you issue a new full IDR request instead. And what is new is that there are some additional methods to avoid that you get excessive data unit queue build up on the sender side. So, oh, sorry, it's a bit slow here. And what is new here is that there is a new metric called queue delay deviation, a normalized queue delay deviation that actually tries to detect when queue buildup starts, and that applies mainly when it's not L4S capable in a network. Then you can get variations in the queue delay because you always try to seek capacity. And that is used for two purposes. One is to get this adaptive reference window overhead. and also to adaptively restrict how much the reference window grows. And it helps to reduce the rate variations and the queue delay when you are not LFRS capable. And in some cases, when LFRS marking thresholds may be high, because we don't have full control of how the network endpoints implement LFRS. You can occasionally have high thresholds and or may not. Ideally, they should be just to ensure high link throughput, but avoid excessive queue delay in the network. And you can also, in cases where you have large and frequent variations in link capacity, which might apply, for instance, for 5G access if you're in a highly varying wireless link environment. And the adaptive reference window overhead, it restricts the burst in flight when you're congested. And that is to avoid that you flood a downstream queue with data and get a lot of congestion marking in return, which might really lead to large rate variations. And it also allows the device to flight to exceed the reference window more when you're uncongested, and that gives a reduced end-to-end delay. And it's a beneficial when you are not congested. And for video applications, for instance, it's quite likely that, for instance, in a 5G environment, that you are quite often uncongested, and then you don't want to delay the media frames unnecessarily much. And one example is that if you, for some reason, use virtual queue LFRS marking, and you start to mark packets before the network is congested, or just below the congestion point. And also this reference window growth is reduced when the queue delay is when you are close to congestion, and it reduces the queue delay. And on top of that, there are some adaptive adjustments of this target rate to avoid that you build up excessive queues on the sender side. And it addresses both if you have a mismatch between the target and actual bit rate, that it can happen in some cases, that you actually get a higher bit rate from the media encoders than you actually asked for, and can happen in some cases. And in some cases, you also have a sluggish rate control, that the output bit rate can lag behind by a couple of 100 milliseconds, and that addresses that as well, and it pushes down the target bit rate a bit to accommodate for that. And also in the draft, there is some description how to fix issues with clock drift that you might get if because of the SCREAM algorithm, that is why the delay-based congestion control actually compares the timestamps of the sender and the receiver for its function. And let's see. Some additional improvements that are likely to happen is that this queue delay dev norm can likely be improved. And currently we have issues where you have a high non-congestion related jitter that can happen, for instance, for 5G access, and occasionally also for Wi-Fi. And we need to fix that to try to discriminate between non-congestion related delay jitter and actual congestion delay jitter. And also we have the clock drift that we need to address. And for instance, for Wi-Fi, you can occasionally have large gaps in the transmissions, and that can give very extreme queue delay outliers. And we have people at Google are trying to fix this, and because they see that in experiments with the SCREAM algorithm. And also they are trying to find alternative ways to fix the compute this congestion metrics here. An additional thing is that instead of having this pacing gain as a function between the target bit and the max bit rate, we actually try to use this congestion metrics instead to simplify the algorithm. And finally, there are probably some additional improvements, albeit there will probably be small improvements based on the pending experiments with the LFRS and SCREAM implementation in WebRTC. that is upcoming, hopefully soon. And for those who want to try it out in a more simple way, there is a web implementation in by the Google WebRTC team that you can get from the latest Chrome Canary builds. And you need to enable it on the command line still. And also you can look at the internals, and there's a lot of metrics actually for how screen behaves, and things like frame rate and stuff, and how the jitter buffer grows and shrinks when you switch on and off LFRS. And for the bleeding edge fans, and I haven't tried it out, you can actually use the libWebRTC and implement it somehow. And there's also a chat group, LFRS in WebRTC, for those interested. And I think as before the last IETF meeting, and about having this as a working group item, and in order to in the long run get it a new RFC that replaces RFC 8298, which is pretty outdated by now. And there was one argument that we only should deal with network congestion control. If I remember it correctly, that we only should deal with network congestion control and not the media rate control in this case. But my experience is so far is that you need to address both, because you have mainly because you are alternative in a rate limited and a congestion limited state when you try to keep the target bit rate as just about at the right level. And it requires some interaction between the network congestion control and the media rate control. And we have had a lot of evaluation in a 5G LFRS product, and there are remote control card emos, and there are some trial test implementations in WebRTC. So I believe there is enough buzz around this algorithm to make it a working group item. And there are some minor changes in the algorithm, but the core part of the algorithm has been stable for quite a while now. Most of the changes are actually based on because of the implementation in WebRTC, where I've seen some issues that need to be fixed. So I believe that was all I had. Comments welcome, I guess.
Can folks hear me? All right, I'll let Stuart go first, but then I will have some questions.
This is Stuart Cheshire from Apple. I just have a question. I think it was on slide 2. You made a comment in passing, and I just wanted to get a bit more clarification. The slide says sender side queue can be discarded if too large. And while you were talking about that, the way you described it is it's common for video systems to decide that if it's too late to display a frame, you may as well throw the packets away. And superficially, that makes sense. If you've got uncompressed frames of video, one frame at a time, and it's too late, then you throw it away. But as you correctly pointed out, if you have an iframe followed by a series of P frames, which are each relative to the previous one, just because a frame is too late to display doesn't mean you don't need it, because you still need it to construct the frame that comes next and next and next. And if you throw it away because you think you don't want it, you've then destroyed your whole processing pipeline, and you've got to start again with a new iframe. So for the sake of one packet that would have been a millisecond late, you throw it away and have to send 1,000 packets to recover the self-inflicted damage. What I was not clear is whether you were describing a mistake that is bad and people shouldn't be doing, or whether you are describing something that you think is good and somehow needs to be accommodated.
I believe it's based on actually what kind of practical experience that is needless to try to transmit an old video frame. But you're right that you can if you have a long time before the next group of pictures, and it's a pretty bad decisions in some cases.
So
Previous.
let me
Yeah.
let me try to ask the question again. So I fully understand that you observe this. What I'm trying to find is, are you endorsing it, or are you pointing out a bad idea that people should stop doing?
I believe it's in the algorithms there is an option to actually discard frames, and it's not documented in the detail how to do it. But I believe it's, as you said, it could be a bad idea in some cases, a good idea in some cases. Maybe need to clarify it in the draft, and as you say that.
Yes, let's clarify, because it was not clear from what you were saying, whether you were saying something descriptive that was merely an observation, or whether you were saying something prescriptive, which is you should be throwing away data that you need, which seems like bad advice. My other quick comment, I think on the next slide, you had some boxes with an arrow with the UDP socket giving feedback.
Here.
You know, that is extreme wishful thinking. That's why I have a draft called Source Buffer Management, saying that you should get feedback from the UDP socket telling you to slow down. So again, I think that's aspirational more than reality. We need that feedback, but it does not exist.
Yeah, originally it was RTCP feedback, but as we generalized, it was to any kind of a transport protocol, like Quick, for instance, and removed it to feedback. So it'd be ACK-frames RTCP feedback. So.
Right. So to be clear, the feedback you're talking about is generated by the logic of the congestion control algorithm itself. It is not coming from the UDP socket. It is a result of computations happening entirely inside that gray box, not outside input to it.
Yeah, it's a bit of a sloppy figure. I will clarify that.
Okay, thanks. So I have a couple of questions, but first of all, thank you, Ingemar, for bringing this draft back and continuing to refine it. We greatly appreciate it. I also love to see a WebRTC implementation in Chrome. Now, remind me, we have an Ericsson implementation and we have a Chrome implementation now, correct? Am I missing any other implementations that might exist? Okay, I'll take that as a no for now. So as you asked about adoption, we have our two criteria in CCWG that I believe you touched upon in your presentation, but let's make it explicit. So one is empirical evidence of safety. And you spoke on various testing efforts going on and the algorithm being well tried out. Do we have slides or any other artifacts that would give us any detail about the testing that has happened and the evidence of safety that we saw? Didn't see it linked out from the slides, but would be interested in that.
I guess you were asking me or somebody else.
Yeah.
Yeah. Okay. And we have a testing data, but it's not published.
Okay.
That is and we have from the remote control demos, remote control core demos. We have some data, and probably can look some of that up, but yeah, that's something I can.
Yeah, thank you. Do you have plans to
Yeah.
publish them?
I need to look at if it's possible to publish it, but I believe the WebRTC testing that should be possible to publish and when that is ready. So,
Okay,
but
great.
look up the.
Yeah. Sorry, and then just trying a time check here because we are still a little bit ahead of schedule, but I would like us to have enough time for all of our presentations. So the other CCWG adoption criterion is stated intent to deploy, and I believe you spoke on that as well, but can you summarize it briefly, please?
I see that you have Harald on the microphone. Maybe he can share a bit information on the WebRTC implementation. And besides that WebRTC implementation, I am not aware of any other implementations or other like applications for that matter. But
okay, and then the Ericsson implementation, you said the 5G product is using it.
Yeah. No, that is mainly running code that is available for anybody who wants to experiment with like a remote control car. And I believe, for instance, we have had a German company way that implemented Scream in their remote control rental cars. Then some of them are running in Las Vegas now, and we have some experiment in Germany pending some approval from the government to deploy that, and they use the Scream algorithm.
Okay, Harald, did you want to speak on that or something related?
So I really got up to make a few comments to Cesar, but I can speak to deployment. We are running experiments on enabling L4S support, and our current congestion control algorithms do not consider the L4S signal. So that's why we're jumping on Scream. And if Scream proves to be good for the general case, it will be better for the L4S case. So yes, we do intend to push this into libWebRTC as the standard congestion control for WebRTC connections, if the experiments prove to be correct. So we have intent. The 2 points to Stuart was that there are a couple of tricks you can do to decide what to throw away, including things that were going on over in AVT core with algorithms and signals for saying, hey, I have this frame, you can now encode according to that frame, so that things can be safe to skip. And the other one, with the UDP socket feedback signal, in the Chrome implementation, the congestion control algorithm lives in the renderer process, which is a bit far away from the network process. And there are some feedback signals coming from the steps between the congestion control algorithm and what the operating system thinks is the UDP socket. So there are feedback signals. It's just that, yeah, it's complicated. Does that answer the questions I was asked to speak to?
So my comment about feedback was based on experience I had. I got in a silly argument with somebody telling me that UDP was faster than TCP, and they demonstrated this by running iPerf. And it turns out that UDP can send 5 gigabits per second over a 1 gig Ethernet, whereas TCP could never get more than a gigabit over the gigabit interface. And without naming names, the platform they were testing on, sending to a UDP socket never returned an error. It never returned any kind of back pressure. It never said the queue's full. It never returned E would block. It was just dev null. The UDP sockets could discard data as fast as you could generate it. And some residual amounts might make it out of the Ethernet port, but the rest of it was being deleted as fast as you could send it. So UDP sockets are a black hole for destroying packets. This is why I wrote the draft for source buffer management, which is at every layer, whether it's Wi-Fi, whether it's cellular, whether it's Ethernet, whether it's UDP, when the queue's full, tell the sender, stop, the queue's full. Do not just be willing to throw data away because you've got a fire hose of data being generated and a fire hose of data going down the drain. And then you've got a bunch of complicated algorithms trying to recover from this self-inflicted mess. And I hope I explain it fairly well in my source buffer management draft, but if anybody designed a serial port or a floppy disk controller or a graphics card that lost data the way network interfaces do, they wouldn't keep their job. And I think we need to fix this.
All right. Stuart, I think for our next steps here, we wanted to take a quick show of hands. So if you haven't joined the Meetup yet, now is your moment to dive for the QR code, the URL, your phone, whatever it looks like for you. And we're going to start by we're going to talk through 3 things. So we're going to start by asking, do we have the time and the interest? Should we bring that up on screen? Do we have the time and the interest to work on things in the media congestion control area? Note that that doesn't mean that this is the only thing that we will work on in this area. And we've talked about this in past meetings as well, where folks indicated that there was generally some interest here, but we want to get a current read of the room. We'll give that a second for folks to register their input. All right, I see Zahed, you're in the queue. Did you have a comment you want to make about the poll?
Yes, Jahed. I'm getting deja vu because I think in the last IETF meeting, we actually asked the same question, and I thought we had a consensus. I was like, yeah, we're interested in doing it. And that's why perhaps Ingemar came with all the different things. I think why you were asking same question again, or maybe I'm completely wrong.
Yes, we have talked about doing work in the media congestion control area. One of the things that we're talking about here is, do we think we have the time and the bandwidth to do so in this moment in time? We've closed out some things from prior meetings that were currently outstanding. And so one of the reasons that we're asking again is because we think that there may be more bandwidth available than there was in the past. So folks who previously did not feel they had bandwidth might now feel that they do.
Well, looking at it, it didn't change anything. But anyway, thanks for clarification.
All right. Our next question is about who's actually read the draft. So notice that this says a version, ideally a recent version, but we're not saying you have to have read the most recent 07 version. But have you read a version of this draft? All right. Oh, a couple more folks. Let's then move on to our last question for the moment, which is going to be, do we think that the working group should use this as a starting point for some work on a Screen V2 style thing? This is not to say that this is the only media congestion control that we will work on as a group, but this is one that we want to invest in, work on doing a bunch of the testing for. I know we've talked a lot about, different ways that we qualify that a congestion control is safe for deployment. is this one of those? All right, seeing a bunch of yes, seeing some no opinions, not seeing any hard no's right now. That's going to be our last question for this one. And we will obviously take a bunch of this to the list after we discuss offline to do formal adoption calls and things like that. All right, thank you, Ingemar. And next up, we have Kazuho to talk to us about rapid startup about congestion control. Here, over there.
That's
Here.
So hello, this is Kazuho, and I'll talk about rapid start. Next, please.
Do you want to use the clicker?
Oh,
Yes, I can give you slide control on the clicker.
The clicker in the room will not work.
Oh, it will not.
Hold that thought for a moment. We'll get you all set up.
Okay, then I'm just gonna do your next slides.
thank you. Right, so I'll be talking about the issues that we face and what we do and the production experience results, and then about considerations. Next, please. Next, please. So what's the issue with slow start? For CDNs, slow start is important because the majority of HTTP connections never is slow start. But there are at least 3 issues. And so let me show it in an illustrative way. So if you look at the very left side at the bottom, as you can see, if we are using slow start, there's moments of idle because pacing only happens for half of an RTT. So the other half of an RTT, the network becomes idle. And the second problem is that 2x growth is too slow. I mean, it can be fast as it can be seen in this example. And the third problem is that when flow start with congestion, the behavior is very, very bumpy. The first sub-problem is that the second recovery occurs too soon because the reduction of the congestion window size is not enough. And the second sub-problem is that queue is entirely drained and then filled up due to reducing C1 by beta. To purpose, the reduction is too sharp and it causes this bumpy behavior as well. So if you look at the blue line, that's the amount of data being delivered, you see 2 dips of the blue line. So that's how the delivery is delayed compared to if it was straight up, then I think fast.
1 second. Are we back? I think we're good. Cool. Please continue.
Thank you. So what are we doing with rapid start? First, well, this is nutshell, but what we do full RTT pacing in the first round trip. Then we do 3x per round trip increase until we see queue build up or until we hit the congestion. And then once we hit congestion, we do a much more quicker and smoother reduction of the congestion window so that the congestion window becomes comparable to what you see during the congestion avoidance. So let's go to the first point, full RTT pacing. And this is what the draft says now. To ensure that path queuing behavior is observed rather than sender-side burstness, the sender should pace the packets over full RTT using the current RTT estimate when it first sends more data than classic flow start with pacing would permit. And this send window can do IW multiplied by 2, assuming that because it yields comparable sending rate compared to slow start, pace slow start, because pace slow start paces packets in half an RTT. So we use 2 times IW and then pace at the same rate. And that gives us 2 times amount of space to send data. And this might sound awkward, but it's actually what a careful resume does with its unvalidated space. So we are simply saying that we could do this using jump C1 of 2 times IW using careful resume. And the next thing we do is the rapid increase thing. So until we observe a queue buildup, we increase the congestion window size by 3x per round trip rather than 2x. And the current graph says that queue buildup should be measured like this. Like if the RTT flow, which is the smallest RTT observed in the most recent 1 hour round trip, is at least 4 milliseconds greater than the RTT minimum, or if it's above 1.1 times RTT minimum, then we call it a queue buildup, and we refer to the 2x thing. Or if it's bigger, then we could go to high start plus style, 1.25x thing. So the idea, I mean, the algorithm can be different, but the basic idea is that the algorithm can stay compatible with rapid high start plus, and we can use the same logic to observe the RTTs, and then decide whether we do 3x, 2x, or 1.25x, which high start plus says. Then, probably the most interesting thing is about handling congestions. So as I said earlier, slow start is not very good at exiting exiting the setup phase because it doesn't reduce the congestion window very well. The problem that occurs unless high start plus kicks in is that by the time slow start detects congestion, the congestion window is already 2 times the full BDP because the sender has used a full RTT for increasing the congestion window. And that means that even if you use the congestion window using beta of 0.5, the congestion window size still stays as large as the full BDP, and that triggers the next recovery period immediately because you see an immediate loss. However, so in terms of correctness, what slow start should do is reduce by beta divided by 2, like 0.25x. But just doing that is suboptimal because if you reduce the congestion window size to 1/4, then the sender will remain silent for 3/4 of the RTT, and it completely drains the queue. So it's clearly suboptimal when we are trying to send as much as possible as fast as possible and have such a silence period. And this problem actually becomes worse with rapid start 3x because in the worst case, you could overshoot by 3x. So instead of spending 4/3 of an RTT being silent, you could spend 5 out of 6 RTTs being silent. And then the burstiness that happens after also becomes much more rapid. So it could induce packet losses other than due to this bottleneck queue. So what are the desired properties of handling congestion? One is that when you enter the recovery, the sender should stop and delay the queue somewhat so that there wouldn't be consecutive losses following after. And when it exits the recovery, the congestion window size should be comparable to what we get during the congestion avoidance. And that is beta multiplied by full BDP. And the third issue, and the third property that's desirable is that once the sender resumes sending after the silence period, it should avoid bursty behavior and it should send at a steady rate. These are the 3 properties that we need. So how do we achieve that? Rapid start uses 3 things. Upon entering recovery, we multiply C1 by a factor called silence factor, and that momentarily stops the sender from sending, assuming that the sender is C-wind limited. And then, and while that's happening, for each act being received, we reduce the congestion window by bytes newly act multiplied by a factor, and bytes newly also multiplied by a factor. And that means that once the sending resumes, the sending ratio becomes fixed, assuming that loss ratio during recovery is uniform. Because the in-flight is reduced by bytes newly act multiplied by 1 and bytes newly act multiplied by 1. So it becomes a constant rate of sending. And these 3 factors, silence factor, act factor, and loss factor, are chosen so that in the case of worst overshoot of 3x, the sender remains silent for no longer than during congestion avoidance. and that upon exiting recovery, the congestion window lands at beta multiplied by bytes act in recovery. And and assuming that all the losses are due to bottleneck queue overflow, bytes act in recovery would be equal to full BDP, so we get right at the correct point. And there's these numbers that the derivation process is being explained in the appendix, but they look like this. I mean, if beta is 0.5, it's like 5 out of 6 or 1 out of 3 or something like that. And if beta is 0.7, it's like this. So let me explain in an illustrative way. This is how we handle congestion. If we look at the left-hand side one, it's the 3x overshoot case. So by the time 0.00 is when the sender notices the congestion. At that point, C1 is 3 times the full BDP. So we reduce the congestion window by 1 out of 6, and the blue line dips a bit. And then, assuming that the loss ratio during the recovery period is uniform, it goes down straight until we end the recovery period. And while in flight goes a bit sharper to the bottom, because in flight is simply a sum of act bytes and loss bytes. And we converge at exact moment where the RTT has 0.5 RTT has been spent. So this is the expected behavior. And using the same constant, if we do a 2x overshoot, it looks like this. So the silence period becomes a bit shorter because the blue line and the red line converges a bit earlier, but we still have enough time to drain the queue. And then the sending resumes at the correct rate. And in either the case, the C1 upon exiting this recovery period is 0.5 times the full BDP, as shown in this chart. And this is the similar chart for the beta being 0.7. And as you can see, both work exactly like the beta equals 0.5 case. And we also have safeguards. We say that the sender should not reduce C1 below pre-recovery C1 multiplied by beta divided by 3. And the rationale is that assuming that all losses are due to bottleneck overflow, the maximum loss ratio is 3x, or 2 out of 3. So therefore, we should only reduce, we should only assume that full BDP is as small as that value. And we also say that the sender may stop reducing below beta multiplied by IW, and the rationale is that on terribly slow paths, we want to play on power with slow sets. So we wouldn't go below beta multiplied by IW. So let's go back to the illustration that I gave as a first study. So this is when what happens when we run rapid start on a simulator. As you can see, the full RTT pacing eliminates the moments of networking idle. And then 3x growth gives us a much faster growth. And as you can see, upon congestion, the congestion window lands at the correct value, and we now only have 1 recovery event compared to having 2. And so the downside is that the blue line, the growth of blue line takes longer because it takes longer to fix losses because we've sent 3x amount of data. So instead of the traditional slow start case that takes 2 RTT to fix the losses, it now takes 3 RTTs. So this is the trade-off that we have. I mean, versus only having one recovery event versus having a bigger one. And as you can see, there's no longer the dip of excessive draining and followed by burst. We land safely at the correct ascending rate. So let's go to the production results.
Quick time check. I noticed there's a bunch of slides left and you have about 2 minutes.
Oh, I see.
Results are fantastic. We love seeing results, so don't stop with the results.
Okay, so this is TTLB reduction in global. So this is about objects above 200 kilobytes. And globally, we see 14.7% TTLB reduction. And for what's worth, the blue line is only doing the first round trip thing. And the yellow line is only doing the rapid increase thing. And the red line is doing both. So as you can see, doing both provides us the best outcome. And we've also separated these results to per POC across multiple continents. Under TTP, LB reduction is like from 10.8% to 21.5%, which is great. And if you look at different object size bins, the smallest growth is when the objects are the largest, and it's like 10.6% for 1.6 megabyte to 3.2 megabyte. And for the smaller size bins, the growth is much, the reduction is much bigger, and we get 14.9% of reduction. And packet loss ratios, as you can see, with rapid start, the packet loss ratio increases at the average of P50, but it's not that big. And if you look at P99, it's almost comparable to when you, I mean, the difference between slow start and rapid start becomes slower, which indicates that when the bottleneck, when the path is very slow, we are not that aggressive compared to slow start. And this is also purple data. And if you look at P99, slow start is doing 19.60% packet loss, whereas rapid start is doing 21.65. So it's the difference is even smaller. So to summarize the production experiment outcome, we are seeing these results, and we are pretty happy with what we are having now. So considerations regarding ECN. There could be considerations, but our understanding is that because ECN reduces the possibility of having losses, the penalty of having a larger recovery period gets eliminated. So rapid start becomes more reliable when ECN is being available. So it's a win. And regarding TCP, honestly, I personally don't know how to do it because in Quick, there's the concept of bytes newly act and bytes newly lost per each act, but TCP might not have it. So it will be up to each TCP stack to do whatever. So to summarize, as I said, rapid start consists of three things: full RTT pacing, 3x growth until queue build up, and then the smoother convergence of congestion window size. And we are seeing strong production results as being provided. So the next steps would be like, I'd love to hear what you think. And it'd be also great if the working group could adopt this, but what our minimum objective is to make sure that the transport community is aware that growth rate above 2x is possible, and we'll be doing that. And that therefore, please don't implement flow control under the assumption that the sender will only increase by 2x per round trip. Thank you.
Thank you. While folks are hopping in the queue, we're gonna also put up our same three questions for this one. Those are some impressive results. So we'll let people talk through some of the queue stuff, but let's get the, and we've got the first poll question up as well. So same questions as before. Again, this is not necessarily the only work that the group will ever do on slow start. Is this a thing that is interesting? I know we've had a couple of other slow start and slow start adjacent proposals in the last couple of meetings. So as we've been looking at the group having more bandwidth, this is the question here. And then we'll go from there. First up in the queue, we have Martin Duke.
Martin Duke, Google. Google, I was very impressed with the way you systematically thought about your goals in doing this and what the end state should be. I thought that was very illuminating instead of just sort of random. So frequently, just like we just wanted to be faster and better, and that was very specific on what you wanted, and that was great. The results are good. I guess what I would like to see is, maybe I missed it, did you make any assessment of how this interacts with other congestion controls that are sharing the same bottleneck?
We didn't do it because this is a startup algorithm, and basically fairness is more about during the congestion avoidance phase. But one thing that can be said is that because we converge much more faster to the correct state that should be gained during congestion avoidance phase, rapid start is, I mean, on balance, well, maybe as good as slow start, even though it does 3x.
Okay, I think it would be interesting to at least see some simulations of like, let's just say that like a slow start and a rapid start happen simultaneously. You know, what does it look like? And the standard does not that it's like completely fair. We discarded that a long time ago, but it would be interesting to at least understand what that looks like. Thanks.
All right, let's close out this poll and put up the next one while we hear from the rest of the queue. Next, we have Antonio.
I put some questions for you on the list, but the one I kind of want to actually talk a bit more here is actually related to 3x growth. I think, as you actually put in the presentation, it's very likely for you to actually overshoot by 3x in the same way that we used to overshoot as 2x normally. Is there anything we can actually do to detect how much bandwidth is actually left in a more systematic way to actually like try to actually not exit early, not exit late from the 3x phase? I think you're muted.
One more time.
Right. So we already have high stop loss and search that can be used to detect queue buildup. And honestly, I'm not sure of the best answer for detecting queue buildup. So what we are doing here is, well, let's just assume that high stop plus has the correct value, and we adopted it, and it's working. That's our state. So it's only a recommendation. So we could just choose that value as we like and see how it goes.
Thank you.
Yoshi.
Yoshi Nishida from UP. So I have one TCP related question. So TCP has a RFC 6675, which calculate outstanding packet and lost packet by using SACBRAC. And so are you talking about 6675 is not good enough for you, or you are just talking about TCP implementation that doesn't support 6675? Oh, I think you are muted.
Honestly, I don't have experience with TCP. All I'm saying is that Quick provides these per ACK byte flow metrics, and that's fine for rapid start. I don't know about TCP. That's what I'm all saying.
Okay, got it. Maybe we need some discussion about offline. And then also, I have one more question. So let's say you have BBR implementation, and then let's say you tune BBR implementation to use real aggressive startup gain and real aggressive drain pacing gain. And does this achieve your goal, or you still need a rapid start?
Right. So I probably say that we have 3 elements in rapid start, and if you could accomplish those 3 properties inside BBR, then it will be qualified. Like full RTT pacing in the first round trip, and then the 3x probabilistic 3x thing, and then the correct reduction of the congestion window size.
Well, then I just would like to understand BBR can do similar job or not?
Well, I'm not sure if I can be confident enough to answer that question. Sorry.
All right, next up we have Neil. We also have our final poll question up, so make sure you take a look at that one. All right, Neil.
Thanks for this nice presentation with some really interesting ideas. I had a couple points and questions. There was a question about whether TCP has the data points that are required for this, and I would say that it does. So Linux TCP, for example, does calculate those 2 quantities that you were mentioning: the number of packets delivered, the number of packets lost on every ACK. So I think I think this would be something that could be easily adapted to TCP. There was one slide early on, I think that maybe had a typo where it was missing a plus character, I think, when it was saying how the sea wind was adjusted. I think maybe it was intended to say sea wind plus equals, like the increment to sea wind is given by the value that's calculated. That maybe just like a typo. One thought on the experiment, it would be nice to, if the experiment slides could sort of document what buffer depth was used for those diagrams, because I think the results might differ quite a bit depending on how deep the bottleneck buffer is. Since there, like, for example, there were some calculations that I think we're setting the C1 based on a multiplicative factor times how much data was delivered, and how much data was delivered could be quite a bit different depending on the buffer size, I would think. And then I share Yoshifumi's interest in seeing what it would mean to adopt these ideas to BBR. It does seem like there's an overlap in this sort of spirit and in some of the mechanisms in terms of trying to be smoother in pacing and trying to, when you realize the pipe is full, you kind of want to pull the amount of in-flight data down to what the algorithm estimates as a reasonable level. And so it does seem like there's some interesting overlap. And it might be something where maybe this algorithm could have different but similar instantiations for loss-based congestion control versus, say, something like BBR. But anyway, thank you so much for the presentation.
Thank you. So regarding the congestion window size adjustment, yes, we subtract them based on the bytes arc and bytes lost. And regarding a second point about the simulation, it's only for the illustrative purposes, and I skipped, but it was set. I mean, the bottleneck Q depth was set equal to the BDP, idle BDP. And regarding a third point, I agree that, I mean, it'd be great if BBR could adapt something like this. And at the same time, I think that for loss recovery based congestion controllers, adopting rapid start would be a good idea.
All right, thank you. We're quite tight on time, so Gori and Lars, if you don't mind making it quite quick.
Yeah, I was going to say thank you and echo again for bringing this here and looking at this. I was curious about your simulation or experimental setup. Did you look at a range of scenarios? Is there a lot more data that is somewhere linkable about the different scenarios for the path?
Right, so we have per pop data and per object size bin data, so we can deep dive into them if necessary.
Yeah, it'd be good to see a ICCRG talk which goes into different bottleneck configurations and different traffic sharing. That would be super good.
Thank you.
Okay.
Hey, Lars Eckert from Mozilla. Quickly, so we have a pluggable slow start framework in the quick stack, and we have a student worker that has implemented the traditional one and high start, and I think search is next, and I'm trying to get him to implement rapid start as well, at which point we will be able to do A/B testing and deployment and share some data, which brings me to the ask. So if you have metrics that you've gathered and you think they're useful, tell us, and we can maybe try to gather the same metrics so we can do apples to apples, because we are not a CDN. So it might be quite interesting. But if other people who work on slow start or have an interest in slow start have metrics in mind that you would like to see telemetry on, let us know too, and like just email the list. It's, I guess, the easiest. Thank you.
Great. Yes.
Thank you.
Please do send requests for metrics to the list. Just leave the camera, it's fine. Also, I noticed there were a couple of people who said, no, we don't think the working group should adopt. So in lieu of having working group time to talk about that, if anybody said no and would like to explain why, please send a note to the list as well, and we can look at that there. Thank you so much. Next up, we have Christian.
Good evening or afternoon, I don't know. So I did a very short presentation at the last meeting, and the chairs have invited me to do a more extended presentation today of the work I have been doing on congestion control, which is basically to do an algorithm that work well with video, but work well with general traffic in general, with a stable throughput, no buffer bloat, low delays, and works well, especially on the networks with a questionable level of services, like Wi-Fi networks that have large jitter and things like that. My other goal is to keep it simple. So the first thing I did was to look at what are the congestion signals that we want to use. It's not the first thing I did, it's basically the result of looking at many experiments. And the first one that comes to mind is absolutely ECN. I mean, for all the reason that people know why we like things like L4S. It's basically because ECN is largely a true signal. I mean, if a router did mark the packet, that means that you should believe them, because if you don't, they can also mark the checksum of the packet and you're going to lose the packet. So there's no question that you are sharing your fate with these guys. So it's good. The problem is that it's not always there. The second signal that I was looking at in order to guarantee short delays was, of course, check the delays. And I worked on that starting last year. And the problem there is that you cannot trust delays. Because many of the interesting links that we see have variable RTTs or have high jitter, or both. And that means that if you try to use that essentially very variable signal as input into a controller, the controller ends up trying to do a mishmash or a filtering of the signal, and it doesn't work very well. So instead, we decided, the reaction was to not try to react too much on delays, but track the max RTT that we observe and use that to size the congestion windows to a size that is acceptable most of the time. We looked at packet loss, of course, and the first thing on packet loss is that you typically have two kinds of packet losses reported by your loss recovery. You have, in classic algorithms, loss reported on timers, and you have, in modern algorithms, loss reported by observing the sequence of packet and reasoning that, hey, if a packet that arrived that was sent 6 packet slots later is acknowledged, your packet is probably lost. And that gives us two very different signals. I mean, the signals that are based on timers are essentially not reliable, and if you use them, you have very often issue of spurious losses and things like that. And in fact, stacks like Mosquick stack implement the FAC algorithm explicitly say that you should not react on the timers on the PTOs. So we track the real losses. Also, we track not so much the individual loss as the loss rate. And the reason we track the loss rate is that the number of individual losses is going to increase considerably with the data rate of your connection. If you are sending many more packets, you are going on average to see many more individual losses. If you track the loss rate, that's basically fair across all the data rates, and that gives you a much better control point. And the final data that we want to track, and that's based on the experience with BBR, is to track the data rate and use it for pacing. It's very easy to track the data rate wrong. We have had numerous discussions about how do you find out that the application was bandwidth limited, for example. We have also issues of jitter. The measurement of the data rate suffers from delay jitter at the two ends of the packet windows that you use to measure the data rate. And it can be very noisy at times. We are basically doing the filtering of measurement that was pioneered by BBR. And also in the design, I try to not rely as little as possible on estimation that the bandwidth was limited. So yes. So the first design choice in C4 is to track the max RTT and the data rate and use both to first set a window that will be the red line in my figure and set a pacing rate so that if you have a high jitter situation, your transition continues through the jitter incident and is not slowed by a congestion window, and then you can continue. The only way to do that is to implement pacing and use pacing as a control, because obviously if you loosen the window control, you have to replace it by something, and data rate pacing is what you want to do. So in the graph, you can see that most of the points, these are the individual acknowledgement and the byte in flight at the time of the acknowledgement. In the case of jitter, we see that the byte in flight at the time of the acknowledgement is large. Most of it is small, and we can have something stable with this kind of control. So C4 is designed to be very simple. We have an initial stage, which is basically startup. You have a recovery stage that comes after either congestion or a probing of bandwidth. The idea being that if you probe, you will only know the result of your probing after 1 RTT when you receive the acknowledgement of the packet that you did send. And so in that recovery stage, we'll be waiting for all the acknowledgement coming from the previous period, which will be an initial period or a pushing period, and measuring the bandwidth, measuring the data rate based on this traffic, but also stabilizing the amount of byte in flights so that we don't build big queues. Then we get a cruising period in which we are working at the nominal rate. That's very similar to BBR-V1. And we use that to assess the max RTT and to detect congestion. If we detect congestion when we are working at nominal rate, we know that the nominal rate is too high and we know that we have to reduce it. If we detect an increased RTT at the nominal rate while not otherwise finding congestion, it's probably that we have experienced jitter, and we use that to assess the max RTT. And then after a number of cruising phase, we go in a pushing phase, in which we send that higher than the maximum rate to see how much goes through and to see how we can evolve the data rate. Now, a little discussion on how much you shall push during a pushing rate. I know that Neil has written a lot about that. Basically, what you want is multiply your standard rate by some coefficient alpha and grow that way. The question is, how do you find that coefficient? How do you find how much to increase? For example, you can say pick the data out of thin air, like 25%, or you can say, hey, let's look at what Reno does, and you do the equivalent, etc. The big question is that if you put it too small, you are going to react very slowly to an increase of bandwidth, and you will not benefit from the increase of bandwidth because you will not detect it. If you put it too big, you are going to build queues. That's very, very visible if you are doing L4S. L4S is doing the ECN equivalent of shallow buffers. So if you increase too much when the network is actually doesn't have free capacity, this shallow triggering of ECN mark will immediately send you back. And since it takes you a full RTT to notice that, you might be building a queue, you might be penalized by the controller. So our design will say, okay, most of the time we'll push at a very slow rate. Like the standard rate will be 1/16 of the data rate. I mean, we add 1/16 to the data rate. And we do that after 4 RTTs of cruising. Then if we observe that we are actually increasing the bandwidth, then we accelerate. We go to the next pushing phase sooner, and we increase at a higher rate. And if that still works, we go another time like that. And if that still works, we go back to initial to startup to reassess the bandwidth. On the contrary, if we don't see the data rate increasing during that probe, then we move back to the probe level 1, or if we add ECN detecting congestion to probe level 0. And that allows us to stabilize, to do the combination of, in most cases, not pushing too much and not causing delay, but if the bandwidth does increase, finding out. We see what that does, and we have simulations like that. We are doing our testing with a lot of a simulator which is built on the Pico Quick version of Quick. We have been using that for a long time for testing the implementation. Each connection generates a Q log. We have a Python script that basically processes the Q log and extracts the byte per second that we are using for the pacing, the RTT, and the bytes in flight and the congestion window. What you see there is that for this multimedia connection, we are not saturating the window except during the peaks of media bandwidth. It's a long connection. It's supposed to last 20 seconds. So you see lots of peaks of bandwidth. And during those peaks, the byte in flight increase a little. The data rate doesn't go down, so we don't see the drift down of the data rate that we see, that we fear in many things, in many algorithms. And the RTT remains pretty much at the mean RTT. And yeah, I mean, I put myself a reminder there. This big bump there in the CWIN is linked to the way we do the slow start, and it should be improved, and I will work on that next. Second example, this is a short connection, not the same time scale. It's using ECN, and basically we see ECN at work. I mean, we very quickly reduce, I mean, the window and the data rate. The data rate is very stable. We feel these little peaks during the probing periods there, and we get a very low delay, and we get a very good usage of the link. So it works well, but that's ECN. Logically, everybody should be working well with ECN. And we have one test that we do for testing the cascade, in which we have a link that starts at a small bandwidth, and a few seconds into the connection, the bandwidth jumps. So it goes from, in that particular simulation, it goes from 5 megabits per second to 10. And what we see is that this cascade stuff that we did actually works. In that particular simulation, it went all the way into the initial thing, which is maybe a bit too aggressive. We might want to fix that. But basically, in less than a second, we have noticed the increase of the bandwidth, and we are back at the new bandwidth. So that's cascade working well. But then, if you listen, you will see that what we are doing is effectively multiplicative increase. I mean, taking the increase as a proportion of your data rate is a multiplicative increase, and it is not quite as fair as doing the additive increase of, say, Reno. However, it has one big property that we like, is that it allows scaling on a wide range of throughputs. So the reason Reno is very fair is because they slow down a lot when the bandwidth increases. When the data rate increases, they don't go up so fast. And that creates this famous asymptotic algorithm, asymptotic fairness, etc. Multiplicative increase, multiplicative decrease doesn't do that. And in fact, if you have MEMD, your condition will typically not converge. It will be a point where you depend on the initial conditions. So if you look at the graph of things like that, and there are many of them in the literature, if you do MEMD, you end up with graphs in which the sharing between multiple collections is showing like some kind of random walk that is mostly dependent on the initial conditions. That's not good. So we decided to fix that. And the way we fix that is by having what we call a sensitivity curve. So basically, in the absence of congestion, we increase the rate by a coefficient alpha. In the presence of congestion, we normally decrease the rate by a coefficient beta. In pure MIMD, these beta alpha are constants that don't depend on the data rate. What we do there is that we modulate that coefficient beta by introducing a sensitivity coefficient, which is itself a function of the data rate. I mean, we implemented a very, very simple curve for now. But the scale there, it goes from 100 kilobits to a gigabit, and the sensitivity increase progressively of that. The result is that a connection which is using little bandwidth will slow down, will not go back so much in case of congestion as a congestion that is already using a lot of bandwidth. And so that introduce a nonlinearity factor in the congestion control, and that results in stability. I mean, these are the same kind of graph. In that case, we see a competition between C4 and BBR-V2. And we see the BBR-V2 is the connection in green here. So it starts later. There is actually a first comer advantage in these things, because the initial condition for the guy was the C4 connection are much better. They have been tuned for the MT network. But because of the curve, we will see C4 going down and eventually getting to pretty much a fair sharing with BBR. The RTT does peak, And the reason it peaks is because the fairness, the fairness only happens when the bandwidth decreases. It only decreases based on congestion control, on congestion events. And in that particular setup, the only congestion events are when the network gets saturated. But we can fix that, like by using ECN, for example. In the case of Cubic, it's not quite as fair. Cubic only get about 1/3 of the bandwidth, and C4 gets 2/3 in that particular setup. I mean, it does depend on the data rate, but I mean, at least it's not starving. We are good. And then if we do C4 versus C4, we arrive to we have a almost perfect equilibrium. Same data rate for the two connections, but again we are at a very high network occupation with high queues. I mean, on the other hand, if we do introduce ECN in the mix, then the sharing remains mostly fair, and the delays tend to go down. I mean, they never go more than about 1/2 of the RTT, of the mean RTT. It might get better if I had a better implementation of L4S. I did one for my simulation. It's not perfect, but we'll work on it. So, I mean, I don't want to take all the time in this session presenting my stuff. I want to give you some time for having discussions. I try to present our big items. I mean, the congestion signals I want to use, the general algorithm, the use of a sensitivity curve, the use of pacing in order to maintain the queue at a reasonable size. It's still a work in progress. We are mostly testing with simulation. I have a draft explaining all the simulations that we are doing. We have to do better in some cases, like the management of congestion during probe. I mean, we have a slightly unfair design right now, is that the connection who is doing the probing is say, hey, I am working at 2 megabit per second. Let's see if I can use 3 for 1 RTT. It does that, and after 1 RTT it says, oops, never mind, and it goes unchanged. But when doing that, it has created a peak of traffic in the network, and that peak of traffic has impacted all the other connections. So I inherited that from BBR v1, but it probably needs to be fixed a little bit. There must be a cost of doing a probe, because if there is no cost, I mean, we have less stability. We have a big delay spike in the initial phase, and I will need to fix that. And we have also what we observe, some kind of bandwidth drift in case of competition. In case of competition, each of the competing connections tend to believe that the other one is that the delay is increasing because of the other one, and we get the delay getting up. The reason we get the delay getting up is that bandwidth evaluation is imperfect. It is inherently noisy, so you will end up with some measurements that are higher than the actual capacity, and that's what causes the drift of bandwidth. So that's also something on which I want to work. There are ideas on how to do that. And better simulations. I mean, I got feedback, and I will use the feedback. I mean, publish more data, further test the simulator. So that's pretty much it. We have a draft with a spec. The spec is fairly short. We have a big paper explaining all the stuff we tried. The reason I did that is because I wanted to have everything public, everything published, so that it could be referenced by anyone who wants. And we have another draft with all the test scenarios that we are doing. And of course, a GitHub depot with the specifications and the simulations. Thank you for your attention. I hope I did not abuse your time too much.
All right, thank you, Christian. Well, folks, hop in the queue with questions or comments. We also wanted to ask one quick poll question just to get a sense of who's read the document. But thank you very much for giving us a deeper dive into how this goes. And first up, I think we have Lars.
Hi, Christian. Lars Eggert, Mozilla. So I didn't make this comment I'm going to make when Kazuo presented, because I feel that the slow start algorithm is just reasonably simple compared to congestion control. I think you really need to get a solid academic paper or two peer-reviewed by the academic congestion control community before we can take this on in the working group. Because there's like decades of history, as you know. And yeah. I don't want us to do, I don't think we're set up to do this. I think it really needs to be the academics that need to review this first. Thanks.
Yeah. Okay. The problem is that I have not been in the academic circles for like 40 years, so. But yeah, we should have a discussion, yes.
Next up, we have Suhas.
Hi, this is Suhas from Cisco. I've been working with Christian to kind of get some real world data and experience. So we are trying to build a Meteor quick stack within Cisco, and our plan is to kind of use C4 algorithm. Because one of the main problems that we saw with using existing algorithms is that under lossy Wi-Fi network conditions, or where the Wi-Fi doesn't have a loss, but it has a huge latency, and then all the data gets kind of sent to you, queued up. And those kind of behavior, we have seen a lot of problems with real-time audio and video calling. And when we're implementing mock stack, that's something where some of this work started. And our personal test and experiments within our stack, the results seems promising. And as Christian said, along with the test simulator, eventually, once we get more into our mock deployment, we'll be able to share some data from the real experiments too.
Christian, this is Neil Cardwell, Google. Thanks for this, a very nice talk. I just had a couple thoughts here. You mentioned some questions about the stability and convergence of MIMD. Are you including BBR class algorithms in those concerns, or do you mean some other flavor of MIMD?
There was definitely the same problem happening with BBR v1, with the result of competition depending largely on the initial conditions.
Interesting. Yeah, if you could share
for the same reason.
Okay, if you could share some examples, maybe or point me to them on the mailing list, I'd be interested. Yeah, I just wanted to mention that. So the traditional concerns that I'm aware of with MIMD, as for example in the Chu and Jane paper back in the late 80s, are for MIMD where you have a window or a rate that is adjusted purely algebraically with based on the radar window itself. I think a lot of and as far as I'm aware of, all of the problems of that are taken care of if you have a sort of BBR style algorithm where the multiplicative increases and decreases are based on the actual delivery rate of the flow, because you have some nice properties there where smaller flows with smaller rates, it's when they make a multiplicative increase, they see a larger proportional increase in their delivery rate, for the same reason why it's easier for startups to grow by 2x per year than it is for very large companies. You know, it's easier to achieve multiplicative growth when you're small. Anyway, so I just wanted to mention that.
Yeah, I mean,
And then,
we could have a discussion about that. Yes, measuring the bandwidth and tuning based on that does remove one of the worst aspect is that the sum of the bandwidth of all the competitors, if they all do that, the sum of the bandwidth is unlikely to exceed the global capacity of the resource. However, the relative share of the competitors, I have not observed a drive to fairness similar to the one you described. I mean, it depends on tuning, it depends on things. You have to do things like random checking of everything to converge and things of that nature. But yeah, and it's a point that I wanted. Basically, I wanted to not rely on chance. I wanted to rely on putting a spring in the spec, so the spring drives you towards fairness. You don't leave it to chance.
All right. Thank you, Christian.
Thank you.
And we have 2 remaining as time permits talks. It looks like time is likely to permit for only one of them. So we'll do a quick 5 minutes of the first one. Both of these and some of the C4 work we're doing as kind of a blended conversation between CCWG and ICCRG, which is not meeting this IETF. So I know we were just talking about that in the chat, but both of these talks are a little bit more in the ICCRG vein, and we will keep everybody updated as to how venues shift around. I believe ICCRG is likely to meet in 126. So we spent a lot of time with the chairs together figuring out how to sort that out. Let's get started here. We've got about 5 minutes, so let's make it snappy there and keep all of our mic comments also very quick, and then we'll be all set.
Okay, thank you. Hello, everyone. This is Zonglun Li from Tsinghua University. And actually, this is my first time to participate in the IETF meeting, so it's a great honor to present our work on the analysis for the adverse effects of LEO mobility on internet congestion control. Next slide, please.
I pass slide control to the clicker, but I can do it too. Okay, I guess the clicker isn't working.
Oh, okay, thanks. So here is the outline. We will begin with why do LEO satellite networks or LSNs matter today, so that the transport relevance is clear from the beginning. Then the second question, what does LEO mobility do to the network path, and what kinds of dynamics it exposes to endpoints? From there, I will try to answer why can these changes mislead existing congestion control? And finally, which is also the main point of this talk, is what design directions should we consider? Next slide, please. So let me first explain about the LSN architecture and its importance. LSNs connect users through a satellite terrestrial end-to-end path. For the uplink direction, it spans user devices, satellite terminals, LEO satellites, ground stations, points of presence, and finally the terrestrial internet, and vice versa for the downlink direction. Actually, in recent years, we have seen rapid growth in the development and deployment of LSNs. Take Starlink as an example. It has reached 10 million subscribers till February of this year, which makes LSN behaviors increasingly relevant and important to transport. So the issue here is not only its importance, but also how transport should reason about paths whose behaviors are shaped by LEO mobility at internet scale. Next slide, please. So what does LEO mobility actually do to network paths? Our main observation based on the measurements from our 3 vantage points indicates that LEO mobility can cause network instabilities such as path change and radio rescheduling. And these changes appear at the endpoints as sharp shifts in available bandwidth, baseline RTT drastically change, and unpredictable packet loss. Looking at the figures on the left, the path may move between different operating conditions rather than evolving within a single one. So this distinction matters because it motivates a more structured view of path behavior than a continuous time window. Next slide, please. So why these changes can mislead CCAs? At a high level, most CCAs rely on interpreting signals, such as packet loss, as indicators of network states, while in LSNs, there are mobility-driven path changes. For example, loss-based CCAs and delay-based CCAs, they may mistake non-congestive loss and RTT changes for congestion. And for model-based algorithms like BBR version 1 and version 3, their historical bandwidth and RTT estimates may become stale across changed conditions. So beyond misreaction, it is that mobility can change the very meaning of the signals which these algorithms depend on. Next slide, please. So far, we have seen that massive non-congestive network variations break the fundamental models or assumptions of existing CCAs. In order to mitigate this issue, one potential way we think is to identify and filter out LEO-induced non-congestive variations. So naturally, we ask, can we identify a path-level signal that indicates when mobility-driven reconfiguration has pushed the connection across a path boundary? Next slide, please. Our answer is yes. And before introducing path-space boundary or PPB, I would like to introduce what reconfiguration means. Starlink's profile shows that because the satellites are constantly moving, the network plans these connections on 15-second intervals. So we refer to PPB as points where mobility-driven reconfiguration shifts the connection into a new path condition. Both capacity and RTT can be fitted as a step function if we align the path evolution with a sequence of reconfigurations. And inside a step, capacity and RTT changes are relatively mild and smooth. Next slide. These two figures are so important, so I just repeat them on this slide. Instead of treating the path as one continuously evolving process, it's more useful to view it as a sequence of phases separated by reconfiguration-driven boundaries. We think PPBs can give senders a cleaner way to decide which measurements still belong to the current phase and which ones should no longer be mixed into congestion control decisions. Next, please. So what path models in LSNs should like? Our intuition is that the physical LEO path can be complicated, but from the sender's view, senders can often view each phase through a much simpler logical view, which is a single bottleneck. So LEO path is better understood as a sequence of bottleneck regimes rather than one continuously evolving path process. Next, please.
Just a quick note that we are in time. So if there's any of the next couple of slides that are the most important, let's hop to those.
Oh, okay. So to conclude, we think that for the IETF community, maybe it's more important to define PPB with well-defined meanings. So there are 3 points: semantic exposure and CCA adaptation. And we think that beyond congestion signaling, transport layer may also need signaling for such path-based changes. Next slide, please. So we hope this perspective can help frame future discussion on transport design for LEO networks. And that's all. Thank you.
Thank you so much. If anybody wants to dive for the queue super fast. Guys, all right, let's wrap ourselves up. Thank you, Stuart, for hopping into the room as a delegate as well. And we will see you all on the list.